Okay, we're going to take a look at graphing exponential functions, but we'll also look at like different types of exponential functions. So we have our function notation. We have some function, we've named it f. It has the argument x, so x is a part of it. Exponentials are interesting because we sometimes use another variable to represent the base. And this would be known as the parent function of an exponential. Now, we've seen parent functions before. We'll say parent functions. Let's do a little overview. Remember, f at x can replace y, but since we're used to using functions now, we're going to try to do that. F at x is equal to x is essentially a linear function. If we go across like that, there's our function. If f at x is equal to x squared, we get the parent function looks like this. It's a parabola. And now I shouldn't be calling all of these f at x. Since I've already called one of them f at x, I'm going to change the names because technically for function notation, we'd have like g at x, h at x. We just use a different letter so that we can refer to the different ones around the page. What other ones have you learned? I think you guys have learned a root function before.
Yeah.
We'll call this j at x maybe. We'll skip over I just because that can sometimes mean other things, which has, we have a root function that looks like this.
Absolute.
Absolute, you learned j, so we'll call
Well, briefly.
k at x, yeah, just to show. So here it is. We have absolute, which is our v looking one like that, okay? And then we have this one, okay? So these are your standard parent functions for these equations. This one here, what's interesting is I can say the function is 2x, or it could be 3x, or it could be 4x, or 5x. And what's interesting is this base is very malleable, but all of these would be considered like the basic exponential functions. It's very common to use 2. It's like one of the lower ones. The reason we don't use 1x, it wouldn't be that, is because that ends up being just a horizontal line. Because no matter what x is, when x is 1, 2, 3, 4, your f at x or your y value is always 1. So you end up with a horizontal line, okay? So 2 is the next biggest integer, so we tend to use that. So what we can do is we can jump over to Desmos here. We can show this relationship. So here's 2, okay? And if you notice, as we change the base, so we've written it out here, f at x is equal to bx, okay? Let's save this little function called functions. There we go. I can constantly change it up, and you'll see it keeps moving. And then we get right to 1. Oh, I almost got to it. There you go. When we're at 1, we get this just horizontal line.
Yeah.
And then it turns out when we're lower than 1, we get this decaying concept. And then this disappears. Negative doesn't even exist here. Okay? So that's a very interesting idea. So what I'm going to do is I'm going to put a bottom on it. I'm going to say this goes from 0 to 10. Okay? So it's mostly going to look like it's growing. This is known as a growing exponential. And then there's a slight moment between 0 and 1 where we have decay, and then there's a whole bunch of options in there. Okay, and we're going to talk about the difference between those two, but I just want to show you that idea that the base can be different all the time. So this is how we tend to represent the base, just as a b. For understanding and so that we have some concrete value, it's very common to use this as the parent function. Okay, now the next piece is you would have learned something called transformations. So I'm going to call this the general equations for transformations. If we have f, okay, I'm assuming you guys used A. Did you use K for horizontal compressions and stretches, or B? Do you know?
K.
K? Okay, so we'll say that's K. We have X minus, is it C or D maybe?
D.
D? Okay, so we'll say D.
Oh, wait. Actually, yeah.
Yeah, in the brackets. Yeah. And then probably C outside, something like that. Okay. I always use A and then B and then C and D. It doesn't matter. What's important is its location in the notation. Okay, this is the general equation for transformations of any function. This f stands for any function. So I could put a root. I could put a root over here. I could put the absolute around this. Could be linear, so it's just power of 1. Could be quadratic, could be power of 2. And in this case here, we have an exponential function. So what we're going to do is we're going to get the general equation for an exponential function, and we'll use base 2. So if we're using base 2, we can still use our f at x here. The a value is a coefficient. It's in front of it. 2 will be our base. All of this stuff that's in the function, for our notation, that lives up here as a superscript. Okay, so we end up with our k, then we have x minus, I should say minus, it technically should be plus d. No. Yeah, you get the phone and the girls have it. So we have k and d, they're in the exponent or the superscript, and then the c is outside of that. Think of that as outside of this. Now, all of these things do the exact same stuff they would in any other one. This is vertical stretches and compressions, horizontal stretches and compressions, horizontal shifts, vertical shifts, all the same here. But our notation's a little different, and we're using base 2 as our parent function. I could use base 3, 4, whatever we want, okay? This is good for graphing it. This will help us in terms of moving things around. So we're going to quickly jump over to our graph, okay? And we're going to say b is 2. I mean, I could have typed it in. I really should have done that. Yeah, there we go. So this is our regular one. Our y-intercept is 0. Sorry. When x is 0, it is 1. So when the x value is 0, it's 1. And we can also get a whole nice little set of things here. Now, we won't use our negatives. We're going to go 0. And I'm going to use 0.5 because that's going to be port 1. And then we go 1, 2, 3. We get some interesting values as we go up. It's a growing pattern there. Okay. Now these x values aren't increasing by the same amount, and that's just because I wanted to show that one value in between here. Okay. Okay. So let's look at our general transformations. If we have an a 2 to the power a times 2 to the power of, and then we would have k x minus d plus c, and I should actually make that a positive. There we go. So I'm going to ask for sliders for all of these. Okay. So the a value, in this current one, the a value is 1. K value is 1. I'm going to say the d is 0 here. And we're going to get that overlapping again. There we go. So that overlaps the red one. So if I want a vertical stretch, I end up with that a value going up. And then if it flips, it goes downward. So it does the exact same stuff. Okay. What's important is the location of that a value. It's kind of in front of our function. We'll put it back to where it normally was, where regular value is. K values or horizontal compressions. If we take a look, this looks pretty similar. You'll see a little bit of a change in this action around the origin, but for the most part, it looks relatively similar. The flip is a bit different though, because it's on the y-axis. That's the major difference there. Let's see if we can catch it. Almost put it back at 1. And then d value, that's just technically being shifted to the left and being shifted to the right. Mm-hmm. It takes a bit. It looks like it's being stretched at a point, but if you finally take a look at it, the whole thing's just moving left and right without any actual general change to it. And C is moving the whole thing up and the whole thing down, which has a very interesting look to it when you keep the original one there. But that's important for our graphing. Oh, I almost nailed it there. Okay, so we have that information. So we've got our general transformations if we want to graph it. The other key piece is the idea of this guy here, which they sometimes call B. The reason they'll call it B is because if B is greater than 1, we have growing. Okay? And if B is less than 1 but greater than 0, we have decreasing or decaying. Decreasing, or commonly sometimes known as decaying. And the reason they use that terminology is because when we talk about exponential growth, we sometimes talk about using financial terms. We'll use like the idea of 1 plus r as some percentage rate. And what is our financial amount growing by? And for decreasing, we actually use 1 minus r, some percentage again, usually. And it could be the amount you're paying off a loan at. It could be decaying of a population. But this ends up being less than 1. Okay? And in this value, we end up as greater than 1. So this is another way we tend to use exponential functions. So this is like a general look at it. We've compared it to some of the other functions that we've used. We know we can technically use different bases. That's what's unique about exponential. We can transform them the way we transform anything else. It's just the notation looks a little different. And when b is greater than 1, we have exponential growth. And when b is, or that base is less than 1 but greater than 0, we have exponential decay. And just to show you what decay looks like, in our case here, we had growth. We'll go back and read that too. Okay, we'll turn this thing off. We don't need this b anymore. But decay could be like this, equal to 0.5 to the power of x. And you'll see that it's got a bit of a different look there. Okay, so growth is the idea as we move to the right, we're going up, 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 up. And decay is as we move to the right, we're actually going down, 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 down. Both of these have something called a horizontal asymptote at 0. They will never touch 0, which is an important piece because you may end up with questions about that. But this represents decay because this base value is less than 1, and this represents growth because this base value is greater than